Back. So today we're very pleased to have the first lecture of this mini course by Dieter Mitsche. And the idea of this event is that since we have so many students around, right? So we wanted to offer two mini courses, one more on the probabilistic side and more on the statistics side. The statistics side is going to be covered by Kevin this afternoon. And so Dieter will be talking about the more probabilistic aspects of random discrete structures. And yeah, well, without further ado, let us have Dieter.
Okay. Thank you, Roberto. The microphone is working, right? Yeah, okay. Yeah, so I was told that the audience is very mixed, so there will be things, especially in the first part of this lecture, which a good percentage of you for sure will know already. I tried to balance it somehow so that at least maybe then the second half of the course, which is rather next week, then will be maybe more interesting. But the first half probably will be boring for some of you, and I apologize in advance for this. Okay, the course will be about discrete random graph models, basically. Let me write it in this way. For networks, so I tried to make a title that is somehow related to the topic of this conference. The course will contain several lectures on different random graph models, starting with the basic ones. So I will just make a short list of the content, what I will doing. The first lecture today and tomorrow, the second lecture will be about the most basic model for these models. They are the Shareni model, GNP. Then I will talk about random graphs with a given degree sequence. And then the second half of the course will be more about models with a geometric flavor. So in particular, I would like to talk about long-range percolation in one dimension. And the last two lectures will be about a way how to show well, I write here just a sharp threshold, which is not clear at this point what I mean by that, for percolation models. And the very last part will be about random geometric graphs which have a kernel. So will be like, right here, kernel-based random geometric graphs. So these will be like models for random graphs that seem as that work as a possible model for networks, and they will focus in all those models basically on two aspects, which will be the connectivity and the existence of a giant component. So whenever mentioning one of these models, the aspect that I will focus on will be, for some of those, the connectivity, and for other ones, the existence of a giant component. Namely, that the fact that there exists a component in the graph of linear size. Yeah, so this means the graph, when is it connected, and when is a linear size component. So some of these models are infinite, but you should think about this as about the finitized version of this. Okay, so that's the plan of this course, to cover only those aspects, or mainly those aspects for those models. So in particular, for those of you that get bored, this should be like lecture 1, 2, 3, 4, 5, 6. This is more or less the idea. Okay. Well, then I start with the first model, which probably everyone here knows, but nevertheless I will recap it. Is the model GNP. People maybe erroneously or maybe call it also the Erdős-Rényi model, who in fact worked rather with G and M in their original definition, or people call it also Erdős-Rényi-Gilbert model. What's this model of? This is a sequence of graphs. Okay, so for each n, the graph on n vertices is as follows. The vertex set is just from. So this is a sequence of graphs, and for each n, the vertices are labeled from 1 to n, and for each pair of vertices, independently, you flip a coin with probability p. So for each I and j, I less than j. So let's say we use this notation that for G is for a fixed graph, we always have a vertex at V, edge set E. The probability that the edge ij is there is P, independently and identically distributed for all edges. So I call it IAD. Okay, and P depends typically on n. P might or might not, P can depend on n. Okay, so this is for a fixed n, and then you take the sequence as n tends to infinity, and we say that G is an element of this probability space G and P if and only if the probability that G is picked for a fixed n is exactly the probability that all the edges of G are there and all the edges of all the non-edges are not there. So we have this. Just a product. E of G is just the number of edges of G. Okay, so it's a product space where for each edge, independently, I flip a coin with probability P, the edge is there, and with probability 1 minus P, the edge is not there, and this is just the probability. This is just a probability space, and picking from there means that the probability to get one particular graph is exactly this one. And we're interested in effect when n tends to infinity. We're interested for large graphs, so networks usually have a large number of vertices, so we're interested when n tends to infinity. Usually when one looks at asymptotic regimes, as n tends to infinity, is the number of vertices tending to infinity, and that properties of graphs with a large number of vertices. So in particular, we use the following definition. A graph property, let's call it Q, it's just a set of vertices, a set of graphs, sorry, among all graphs on n vertices. So you can think about n as fixed, but then making it larger and larger if you don't like to think about this as a sequence on the vertex set 1 to n. So for example, like the property you have some graphs. Q could be like containment of a triangle, or is the graph contains a triangle. That could be one property. Yeah, there is a set of graphs among those graphs on n vertices that will contain a triangle, and there is another set of graphs that will not contain a triangle. So this is a property, and we care about properties that do not depend on the particular labeling of the vertices. Okay, so in principle you could say, okay, I want label 1 to be connected with label 2 and with label 3, but we will care about properties that will not depend on the labeling. Other properties that will be interesting in the sequels, for example, the graph is connected. Meaning that there is a path from every, this is a connected graph on 4 vertices, and this is a non-connected graph. Well, this is clear for everyone, right? Or Q3, there is a giant component. The graph contains a linear-sized component. The graph contains a component which has at least Cn vertices for some and there's one connected component, say this one, which has at least a linear number of vertices. These will be the properties we will use, or we will look at in particular. And we say that a property Q holds asymptotically almost surely or just AAS if the probability that one graph picked in this probability space contains the probability Q tends to 1 as n tends to infinity. Okay? Now this is for those coming from measure theory background, and you might be confused maybe at first sight because the word, if you don't see this word asymptotically here, you see here only almost surely, but this is really just convergence in probability here. So because of this confusion, notational confusion, some people call it also with high probability, the same thing, they call it with high probability, or WHP. And then there are other people that then complain that how high can it be? That's what Andrzej Ruciński complained once at me. So I prefer to use, therefore, asymptotically almost surely, although it's a convergence in probability. Okay, and we will always look at the asymptotic regime in the sense that we look, okay, we get a sequence of n getting larger and larger, and we want to know when we pick a graph in this space, does it contain such a Q or not? Of course, there's always a chance that even for a very large P, you can always get a graph that is not connected, or even for a very small P, you can already get a graph that is already connected. But we look at typical properties, properties that hold for a typical graph. Okay, that's the main idea. And one phenomenon that often happens with those properties is that there is a sort of threshold phenomenon. Which can be sharp or not sharp, but usually there's a sort of threshold, which I define, for a the sequence of probabilities Pn, the sequence again for different values of n is a threshold, and I define it just for a monotone increasing property, for a monotone increasing property Q. Well, let's put a star here. Property Q. Where monotone increasing just means that whenever I have, for example, a graph that is connected and I add more edges on the same vertex set, the graph remains connected. So I cannot destroy my property on adding edges. Yeah, that's, for example, if I have already a large component and I add edges, well, then the graph still will have a large component. If the graph is already connected and I add edges, the graph still remains connected. That's a monotone increasing property. Decreasing is the same way. But if we have a monotone increasing property, like the ones that are mentioned in this example here, then we say the sequence Pn star is a threshold if the probability that G in Gn Pn contains Q tends to 0 for Pn asymptotically smaller than Pn star, and also the probability that G, this is just one G, G picked from this model contains the property Q tends to 1 for Pn asymptotically much larger than this threshold. Is this okay? This notation here. So this means that here, if I'm picking a sequence that grows asymptotically smaller than this threshold value, then asymptotically almost surely a graph picked from such a model, n vertices and Pn, picked uniformly in this space, the probability that this contains the property will tend to 0, and if on the other hand the Pn is asymptotically larger than that, meaning that the limit of this value divided by this value tends to infinity, here it tends to 0, then here it tends to 1. Okay, this is the definition of a threshold in the GNP model, and there is a result from the 80s which I won't prove now, but whenever you have a monotone increasing property Q in GNP, or whenever you have a monotone decreasing property Q, then a threshold exists. This is by Bolovash and Thomason. I think it's from 86. Every monotone property, either monotone increasing or decreasing, has a threshold. In that sense. Okay, so if I take, what this basically means is that if I make a picture here, and I make here P, and here the probability that the graph contains Q, here is 1, and here is 0, there is somewhere a threshold Pn star, and basically there's a small window around this critical point. I'm exaggerating it a bit, such that here the probability is 0, and here the probability is 1. And there it, in the case of monotone increasing, yeah, Q increasing, otherwise it's the opposite. And here it jumps like this. There's much more precise results are known for many properties, in the sense that, I will just make this in red. There's also a definition of a sharp threshold. I'm adding this just in red for sake of completeness. And then you can say even for Pn smaller than 1 minus epsilon Pn star. So for every epsilon strictly positive, you can replace this. If you replace this by the following conditions, then you say there is a sharp threshold for a property if for every positive epsilon and Pn smaller than 1 minus epsilon times the critical value, the probability tends to 0, and for 1 plus epsilon, the probability tends to 1. Well, if this is true, then you have a sharp threshold for a monotone property. But not all properties have sharp thresholds. There are properties that have sharp thresholds, and there are properties that have coarse thresholds. So there is a nice result by Ehud Friedgut and Gil Kalai that characterize more or less properties that have a sharp threshold. On a rough level, you can think of the following: a sharp threshold exists if and only if the property is global. Yeah, so if you have, for example, if something depends only on 3 vertices, like this property to contain a triangle, this will have a coarse threshold. But if you look at properties that are more global, like the property to have a giant component, or the property of being connected, as we will show later on, they will have a sharp threshold. It's not yeah.
Is there an example where we know what happens in the critical parameter?
Yes. So, okay. Which example? For example, okay, let me give a simple example. Okay, since I mentioned the graph contains a triangle, let me elaborate on this example. That's a bit. Okay, so since we have since I mentioned this, okay, let's make an example here. Okay. Okay, example. Let me take this property Q1. Q that G contains a triangle. Okay, so the first question is, okay, where will this threshold be? Well, the threshold is typically there where the expected number is 1. This is up to a log n factor correct, as was recently proved. So you can, let me call x, for example, the random variable which counts the number of triangles in G chosen from G and P. Okay, so you can compute the expectation. Okay, how many triangles you'll have? Okay, you have to pick 3 vertices. That's your number of choices, and for each fixed triple of vertices, the probability that the triangle is there is p to the 3. So if you want to follow this intuition, okay, when will the first triangle appear? Well, when in expectation you will have 1, right? So in expectation you have 1. That means that p is roughly 1 over n, yeah, for n large. So this is, or let me put a constant here, right? There is, this is 6, constant over n. It's not the constant is not important because we have a coarse threshold here. So roughly at a scale of 1 over n, we will see a constant number of triangles. Okay, so then you can show, for example, so if Pn star is a sequence, if Pn star, for example, is like 1 over n, then you can say, okay, what happens if I pick my P smaller, asymptotically smaller than 1 over n, say 1 over n to the 1 plus epsilon here? Well, for Pn smaller than Pn star, the expected number of triangles tends to 0 already, right? And then you just apply Markov's inequality. By Markov's inequality, the probability that x, which is a natural number, is at least 1 for such p also tends to 0. Okay? And on the other hand, for Pn asymptotically much larger than Pn star, well, in principle, it could happen, right, that with just a small probability you get many triangles, and with constant probability you get 0 triangles. But you can rule this out easily by a second moment method. Yeah? For compute the second moment, shall maybe. And then compute the variance and apply Chebyshev's inequality. So you can compute the expected number of pairs of triangles, which, let me write it pictorially. The expected number of contributions. Okay, how can you have pair of triangles? Well, of either, well, the triangles can be disjoint. Let me write like this. Plus those that share maybe one vertex, plus those that share 2 vertices. Yeah. You compute this, and you see, this is not hard to compute, right? For example, here you have to, for this, we'll get a contributions, n choose 6, p to the 6. Here choose just 5 vertices. And this is 4 vertices here. Or they might just collapse, which is just one single triangle. Yeah, so typically it could also be this. If you add this up, and if you're above this critical value of 1 over n, well, then you see that the dominant contribution is this one. Okay, so for the regime we look at, and the first contribution is the principal one, principal contribution. So we get in particular that this expectation of x squared is up to smaller order terms, which come from this contribution, the fact that this is not exactly n choose 3 squared, the same as the square of the first moment, and that means that the variance is small. And by Chebyshev's inequality, the probability that x is really greater than 0 in this regime then tends to 1. Okay, so this was to give a first part before answering your question, but also to give an example of a threshold where we show by a first moment method. There's a first moment here. First moment meaning I'm computing just the expectation and I apply Markov's inequality, gives you one part of the statement, and the second moment, computing the second moment, by a second moment method, you get you show that the variance is smaller than the expectation squared, and then apply Chebyshev's inequality to show that really with not just with positive probability, but with probability tending to 1, you will have a triangle. Okay, so that's what happens if you're above and below these values. But since you asked me what happens at this threshold, well, let's see. You can choose now P to be a constant over n. If we are right in this regime, okay, then you can do all these calculations again. In particular, you can compute the kth factorial or the kth moment. So you can see that for any k, the expectation of x to the k, when you do the same for any fixed k, you don't count pairs of triangles, but you count triples, you count 4 tuples, you count k tuples. The expected number of k tuples, well, it will be roughly c to the it's c1 to the k for some constant c1, which is it the same? I didn't do is it the same as this c here? C cubed over c cubed, right? Yeah, I think so too. Over 6 or yeah. Okay. Yeah. Okay. So for every constant, you see that the expected number of triangles to the k, or the kth moment of this random variable, is a constant to the k up to smaller order terms. So in particular, you know that when you have a random variable such that its first moment is c, the second moment is c squared, the third moment is c to the cube, and so on, well, then you have a Poisson random variable. Okay? So in particular, the Poisson random variable is determined by its moment. So at this point, at this value, x follows a Poisson distribution with parameter c1. So I'm finally answering your question. So at this threshold, so in this regime, when you have a coarse threshold, here somewhere in between, well, you have a Poisson distribution. So the probability that you have exactly 0 triangles is some constant. It depends on this C1, but this is really something that is continuously increasing, so there is no jump phenomenon. And this is because a triangle is something that is very local. So it depends only on 3 vertices. So if I'm changing my graph a lot, well, there's a certain, it might not matter too much. So there's a certain robustness, and it does not drastically change. Okay. So if I'm asking for example, a connected graph, then this will depend on all vertices. If I'm asking for a giant component, this will also depend on all vertices. And there I will have a threshold window, which is the red one in there. It's not always clear whether or not, for example, whether or not there exists for a given property a sharp threshold. But the idea is that local properties have a coarse threshold and global ones don't. Maybe, yes. Okay. Yes. Okay, so x times x minus 1 times x minus k. Was the same question? Yeah, okay, yeah. Yeah, this was. Other questions? Okay, so this was just to explain the possibility of sharp or coarse thresholds, but for the properties we look at now, namely the property of connectivity and the property of having a giant component, we'll have a sharp threshold, and we will prove this. Okay, so. Okay, so property of now, let Q be the property now of G and P is connected, meaning that I can find a path from every vertex to every other vertex. And we'll show the following theorem. Let G in G and P. Well, then Q has a sharp threshold at log n over n. Log being the natural logarithm. Okay, so in particular, this means that, so if, what does this mean? So if for every epsilon greater than 0, if P is smaller or equal than 1 minus epsilon log n over n, the probability that G contains Q tends to 0, and for every P that is larger than 1 plus epsilon log n over n, the probability that G contains Q tends to 1. This is the another way of writing the same thing. Okay, so if we want to prove, then we have to prove both both parts. So we have to show that if you're below 1 minus epsilon log n over n, then you won't have connectivity. So in a picture, it means that if I have here log n over n, so this is P, and the probability that G contains Q, well, this undergoes a sharp threshold at this point, so it's basically going at 0 here, and then it jumps immediately almost to this line here. Well, then, of course, I mean, as usual, what people are unsatisfied with such results, and then you want to know, okay, imagine the first order term is something like this. Okay, then people look at more precise results. Well, right, then you can say take Pn to be log n over n plus some smaller order term. And then as a function of this smaller order term, you can be more precise. So then you will see some sort of continuous transition on a different scale. I don't want to go into detail, but it's always the fact, it's always when you, on one scale, you don't see anything. So if I'm just saying, okay, my first order term is this, but then imagine you write something that is here, something like, I don't know, log n over n, just to give an example of something. Then perhaps depending on the C here, you will see a more continuous transition. Okay, it's the same whenever you see, well, that's whenever something is known on a certain scale, well, then you zoom in more, and so then until you see something. That's what often happens.
I have a question. In this case, is it known? What
Yes.
The triple parameter?
Yeah, this is known. So there is an e to the minus c, I think, Poisson probability for depending on this c here. So, but that's well studied. So this is well known. Okay. So what is what do we have to show? Okay, first we have to show that, okay, the first part is that if P is smaller than 1 minus epsilon log n over n, then we have to show that the graph will asymptotically almost surely not be connected. Okay, how can a graph not be connected? Okay, you can imagine that there is different parts, right? You could here have one component, say C1, and here have another component C2, and have no edge in between. Or you could have maybe one small component, just one vertex, for example, or 3 vertices or 1, and here the remainder, and here a large component, and only this. So here are edges in between, but nothing in between. But here is just one single vertex that is isolated from the rest. And it turns out that in many models, well, not all models, because some models forbid isolated vertices. If I say that, for example, every vertex has to have at least degree 2, if every vertex has at least degree 2, then this cannot happen. But if I'm saying that, let me pick a G and P with that probability, then it turns out that it's much easier to have just one vertex isolated from the rest. So if someone is, so I know if you have 2 big countries, Brazil and Argentina, then the fact to have no connection between them is much harder than the fact that there is maybe Andorra and here you have France or something like this, right? So this is much, you don't have to block so many access routes in that sense. So it's in many, but not in all models, but in many models it's the very last edge, which is the edge that makes the very last edge that such that no vertex is isolated anymore, namely this one here in this case, makes the graph already connected. So there are very precise hitting time results, more precise than these, which say that with high probability, at the moment when you can think about this as a process, right? You can think about GNP as a process where to each edge you associate a number, and then you look at the numbers ordered from 0 to 1, right? So you could think about it here as a process 0, 1. For each edge you associate a random variable. These are all these joined with probability 1, and then you pick here a value which is, say, Pn, and you include in your graph all these edges that are below this number. That's an equivalent model. And you can think about it in the following way. Okay, order these edges starting from 0, add edge one after the other until this point. And if you're not yet connected, well, then it's most probably because you have an isolated vertex. And if you go in this direction, and there is one last edge that the last vertex is not isolated anymore, then at that point, you will typically already be connected. And that's of course, not deterministically, because something like this could happen, but with probability tending to 1, the hitting time, so the time until how far you have to go until the last vertex is isolated, will be exactly the same as the time when the graph becomes connected. Okay? And therefore, well, if we have this in mind, that probably a small country is the last one to be absorbed by a large country, well, then one can say, okay, let's just compute the number of isolated vertices. Okay, let x here now the random variable which counts the number of isolated vertices in my graph. And you can do the same first moment and second moment analysis for these isolated vertices, and you compute the expected number of isolated vertices. Well, you have n vertices, and the probability that one particular vertex is isolated is the probability that all of these, let's say the vertex n for simplicity, the probability that this one is isolated is the probability that all of these n minus 1 edges are absent. So you get this expectation. And by first and second moment argument, by first and second moment argument, this log n over n is a threshold for this property, is a sharp threshold, threshold for the event that x is positive. Okay, meaning that if I'm, okay, this is a decreasing property, but it means that if I'm below, if I have this, if a probability that is below this number, well, then I will have isolated vertices with probability tending to 1. And if I'm above this number, if I'm at 1 plus epsilon log n over n, then I will not have isolated vertices anymore.
This is not enough to show that it's at threshold yet, right?
This is showing that, so for which property? For this property?
To show that we have isolated vertices.
This is for the first part, Okay. So if I have an isolated vertex, well, then my graph is not connected, right?
Because you wrote that it's enough to use this random variable and first and second moment to show that PM star is the sharp threshold.
For the first part. But this is the sharp threshold for the property of having isolated vertices. So if I'm telling you, okay, I know at this point, if I'm below that value, I have isolated vertices. Well, this is a decreasing property. Okay, then I have isolated vertices below this number, and I don't have them above. What you mean, probably, is that the proof of the theorem is not finished yet.
Okay, so you're saying that the property to have isolated vertices?
This property has a sharp threshold at this point. Yeah. So this property has a sharp threshold, tells you half of the theorem, but not the full theorem. So this tells you that if I have an isolated vertex, then my graph is not connected. But if I don't have an isolated vertex, I cannot conclude that my graph is connected. Right? So that's why I said here, okay, the first part, and the first part follows just from the fact that there is that there is an isolated vertex. So if there is an isolated vertex, then there is no connected graph. But for the second part, theoretically, there could be some component of size 2 which is not connected to the graph, or 3, or whatever. So we have to show that the probability that there exists a subset of the vertices of size k, where k is between 2 and n², say, and S isolated from the rest also tends to 0. If we can show this theorem, that if we can show this theorem, then we know that the graph is connected. Because if there's no component, well, we know already that there's no isolated vertex. But if there is no component of size 2 up to n², then every component has to have at least size n² plus 1. But there can be only one such component. Okay. Okay, we may assume, and how do we show that? Well, we may assume that S is connected, because if S is not connected, well, then there exists a smaller subset which is connected, for which this is hold. This will happen. So we may assume S connected. So if it's connected, then it has a spanning tree on its vertices that is disconnected from the rest, meaning that S has a spanning tree, a tree spanning all the vertices of S, and disconnected from the rest. Okay, so then we can just take a union bound. So by union bound, therefore, the probability that there exists such a set S is isolated. Well, it's at most the sum for 2 up to n². Okay, I have to choose my set of vertices. if I have my set of vertices k here, k vertices, then these k vertices have to be disconnected from all the others. So here's my set of k vertices. Here are n minus k vertices. So all these edges have to be forbidden. So there's k times n minus k vertices that are forbidden. And each of them is forbidden with probability 1 minus p. So these are the forbidden edges. I have fixed so far only my set of vertices, but I haven't said yet what is my graph on these vertices. So I have to fix also a spanning tree on those vertices. I have k vertices. You can use Cayley's formula, which tells you that there are exactly k to the k minus 2 many spanning trees for a fixed set of, say, something like this. For all those k vertices, you have to find a spanning tree. If there are additional edges, we don't care about them. They might be there or might not be there. We just identify each subset which is with its spanning tree. But a spanning tree has to be there. And once we have a spanning tree fixed on k vertices, well, the spanning tree has k minus 1 edges, and these edges have to be there, right? So there's another p to the k minus 1 here. Okay. Well, and this is a little bit of calculation, but not too hard here. I will not. So the case k equals 1 was already done in the first part, and you can see actually that the hardest part here, or the highest contribution of this sum, comes for k equals to 2, which will also tend to 0. And then you can, for the others, you can even obtain a sum that nicely converges. And believe me now that this tends to 0. Okay? This is a little bit of calculation, which just, what is the essence of these calculations? What can you do here is, well, you use this kind of estimates. I'm not going to do this now, but you use this kind of estimates, and you can convince yourself that this tends to 0. Okay. So this shows that at log n over n, the property of having a connected graph has a sharp threshold. So if I'm taking a larger probability, then this will happen for a typical graph chosen from G and P with P larger. You will have a connected graph, and for P smaller, you won't have such a connected graph. And since I mentioned the connected graph, I will just, before entering into the giant component proof, mention this for a different random graph model as well. The threshold for here, of course, depends on the model. I could look at a different random graph model, which I call now an interlude, which is not GNP, but it's just simple random geometric graphs. Which is a different model of random graphs, where in the simplest model, you do the following. You have a square 0, 1 squared. And the vertices will be the positions of n points thrown uniformly at random in the typical model. Yeah, so you can say, okay, I have vertices numbered from 1 up to n, and for each of them I choose a random position. I choose a random position, I choose another random position, I choose another one, and so on. So the vertices are positions of n IID uniform points in the unit square. So there are n positions, and I identify those points, the positions of those points, with the vertices of my graph. And the edges will be the following. So let me make a few more here. Okay. And we say that, for example, this is vertex I here, and this is vertex J. And we say then, once I fix these points, the edges are deterministically present or not. We say that I and J is an edge. So here's also the same model with vertex set V and edge set E. If and only if the Euclidean distance between I and J is less or equal than some R. So here we had a parameter in this model that was P, the probability, and in this model the parameter is a radius R. So we call this model usually the GNR model. For a fixed R, well, R again might depend on n. You put an edge between two vertices if and only if the Euclidean distance is less than R. So for example, if this is my R here, if this is my R, then whenever the distance between those is 2 points is smaller, I put an edge. Okay, maybe something like this. Okay, maybe this is another edge here. Okay, so this would be my random geometry graph in this model. This is a different model from this model. So here I said each edge appears independently with probability P. There is just no dependence at all. But you might think of, okay, in a real world network, for example, in Facebook, if I'm telling you, okay, you're a vertex and you're a friend of another vertex, okay, then the edge is there and this other friend has another friend, well, then the probability that you're also a friend of your friend's friend is not independent of the probability that you're a friend that this guy is a friend of him. So there should be some dependence in the edges. That's why this model of, and among other reasons, but why this model of Erdős-Rényi graphs is maybe not the most useful model for modeling networks. It's mathematically the most natural model because it's the most simplest and nicest to analyze. But there are other factors sometimes that, well, if you're physically or geographically close to someone, then there should be some effect of geometry here in the sense that, okay, if you're close to each other, then maybe it's more likely that you're friends. So it's more likely that you have an edge. And the first model, which kind of improves on this in that sense, is this model of random geometric graphs, because here you have this this spatial dependence. Okay? I'm not saying that this is a good model for random networks. This was just the second model in the course of history, which came from sensors used in telecommunications. So where these are antennas, and you put an edge if they shouldn't use the same frequency. But it's already a first model where you can see, okay, the same analysis that worked here for just counting or the number of isolated vertices, or for showing connectivity will not work here because the dependencies here are different. Okay? And then, of course, you can ask the same questions for this model. Okay, here we said that there is a threshold probability P such that if P is smaller than this, well, then you will have an edge, or what would be the analog here? You could ask this question. And here the question is in this parameter here, of course, right? If you make your radius much larger, if I'm changing from R1 to a number R2, well, then I'm having all the red edges, but I'm adding blue edges as well. And at some point, I will get a connected graph. So you can ask the same question. Okay, what is the smallest? You can ask the same question. What is the smallest? The smallest radius what is the smallest radius? And again, the radius will depend on n. So you can define again a threshold Rn star in this way, such that for Rn asymptotically much smaller than Rn star, probability that G now in G and R contains the property Q, Q still being the property of being connected, tends to 0, and at the same time the probability that for Rn asymptotically much smaller than Rn star, the probability that G picked from a GNR model contains the property Q tends to 1. You can ask the same question, what is the smallest radius? So you can think of well, you can think about those radius like drawing balls around each vertex such that you obtain a connected graph. Okay? It's known where this happens. It's known that there is a sharp threshold. I will not prove this theorem, but I will just mention it. Theorem. If you're in the unit square, and if you use the Euclidean distance, so meaning balls of radius r around each point, the value of r n star being root of log n over n pi is a sharp threshold for the property Q for the probability that G in G and R or Rn contains the property Q. So if I'm taking, so I'm by symmetry with the previous result, I'm just writing it for Rn smaller than Rn star, probability that Gn Rn connected tends to 0, and for Rn much larger, well, actually I can put here 1 minus epsilon, and here also 1 plus epsilon Rn star. The probability that Gn Rn connected tends to 1. Okay. Well, just a comment on the theorem. Will not really prove this because my time is. We started at time, right? We started on time, right? Yeah. So then I'd rather stop here. Just a comment on the theorem. In this model, it also turns out that isolated vertices are the most important obstacle for having a giant component. Isolated vertices are also the most important obstacle for a giant component, for connectivity, sorry, for connectivity. So what you have to do is, well, just a picture. When is a vertex isolated? Well, you take the vertex and you look at a ball of radius r, like this, and there should be no one else inside, right? So if I'm counting the number of isolated vertices, then I'm counting just the area of this point, well, the area of this ball, which might intersect with the boundary. One has to be a bit careful, but let's suppose not. Well, the area of this ball is r squared pi. So the area of the ball centered at V of radius r is r squared pi. And you want the probability that this area is empty, right? So all of the other n-1 points, they should fall outside. If that happens, then this vertex is empty. It turns out that for analyzing this, it's much easier if you do it in a Poisson setup. So instead of picking n uniform points, you do a Poisson point process. So where you say, okay, with the same uniform intensity n, you choose your points in the unit square, because then you can immediately see, okay, for a vertex to fall into this area, that's just the probability of this area. If this is 1 here, this area is 1, well, then this area here is r squared pi, and the probability that the vertex falls inside is r squared pi. So the probability of another vertex, or that, let's write it in this way, that V isolated is the probability that all n-1 other vertices fall outside. This happens with this probability, and this has to be true for all n-1 other vertices. So the probability that one vertex is isolated is this, and then you can compute the expected number of isolated vertices. The expected number of isolated vertices is just the same number just multiplied by n. And then you see if you plug in r here being the square root of log n over pi, well, then this number gets 1 basically. And then we have, as before, an intuition where the threshold could be. That's where the root of log n pi, so the pi cancels, and then you get what you would be thinking intuitively, namely that the threshold will be when the isolated vertices disappear. And it turns out that, as in the case of GNP, to have components of size 2 or 3 is harder. So that requires some extra work, which I won't do now. But again, the hitting time, which in this case is the radius, so the last radius, which makes the last vertex non-isolated, will be with high probability also be the last, will be exactly the same radius for connectivity. Okay, I stop at this point today.